Now let's talk about how we can convert from FLTs to maps on CP1 that better capture their behavior. So recall FLTs are of this form, where A, B, C, D has non-zero determinant. In other words, this is invertible. We can convert this to a function from CP1 to CP1 via this formula. And this agrees with our original definition because points in C, so of the form Z1, get mapped to AZ plus B, CZ plus D, and when the bottom is non-zero, you can convert this into what we had before. And so it agrees with the function f of z when everything stays in C. But the nice thing about this formula is that we don't have to worry about it. And we do have to check that it's well defined. So if I take f of z1, z2, does this agree with taking a different representative? So if I multiply through by a lambda. And of course it does, because my formula is linear, so putting a lambda in here will just take a lambda in front of everything. So that's no issue. And you'd also need to make sure that you don't ever get 0, 0, which is not in CP1. So can I ever have both components 0? But since this matrix is invertible, that happens if and only if z1, z2 is 0, 0, which is not allowed in the definition of CP1. So this is well defined. It maps from CP1 to CP1, and I don't have to worry about what the domain and range are as I would in the case of the complex numbers. I don't have to make special cases. And it's clear, given one of these, you can convert it back the other way just by following a procedure similar to this. One nice thing we get out of this approach is that we can describe all FLTs using matrices and an equivalence relation on matrices similar to how we define CP1. So if we take a 2 by 2 matrix, which is in GL2C, and recall this is just 2 by 2 invertible matrices, we can define one of these FLTs on CP1 using just matrix multiplication, and it's really no different from what we've been writing before. But now we can begin to use properties of matrices to study FLTs. So a homework exercise is to show that FA is identically equal to FB exactly when these two 2 by 2 matrices are multiples of each other. And this means we can identify two FLTs using some equivalence relation on matrices. So the set that you get is called PSL2C, and this consists of all 2 by 2 invertible matrices with an equivalence relation, where the equivalence relation is the same idea that we used for CP1. So A is equivalent to B if and only if A is a non-zero multiple of B. So why is it PSL2C and not PGL2C? Well, each A is equivalent to this matrix here, where we renormalize it so that it has determinant equal to 1. And so PSL2C is actually equal to the set of all A's in SL2C. So this is 2 by 2 matrices with determinant equal to 1. And so this is basically the same as SL2C, except two things in here are equivalent if up to a minus sign. So this is the only redundancy when you use this model. So A is equivalent to minus A when A has determinant 1. So now, with this description, we get basically a theorem from using all the right definitions. Each FLT from CP1 to CP1 corresponds to exactly one element of PSL2C, so that each F can be represented as one of these FAs. Now, just staring at the definition of FA, you immediately then get that a composition of two FLTs amounts to a matrix multiplication. So if I plug FB into FA, you're going to multiply the matrices and you'll get the FLT given by FAB. And from this, you get that all fractional linear transformations are invertible, and their inverse is given by taking the inverse of the corresponding matrix. And you also get out of this that FLTs form a group under composition. Let's look at some of this with the example of the Cayley transform. So the Cayley transform was this map, f of z is I times 1 plus z over 1 minus z. We can convert this to CP1 world, where I have sort of a typo in here. Now, so little f converts to this big F of this form just by looking at the matrix you would use or the coefficients. And so big F has the matrix I minus 1, 1. So F can be represented with FA. And from this, we can compute the inverse of the Cayley transform. Well, I can do that by just finding A inverse. And it's even easier than finding A inverse because if you use Cramer's rule or the formula for the inverse matrix, you have to divide by a determinant. But since this equivalence relation doesn't care about multiplying by a constant, you don't even have to do that. So you just use the usual formula for the inverse, but you forget about the determinant in that formula. And so you get, well, the way you remember it for 2 by 2 matrices is you switch the elements on the main diagonal and then put minus signs on the off diagonal, and you get immediately what the inverse map is of the Cayley transform. So it's given by this formula, and then you can convert this back to just complex numbers to see that it has the formula z minus I over z plus I. So here, if we were just sticking to complex numbers, we would need z to be not equal to minus I. And back up here with the original f, you would need z not to equal 1. But over here in this model, we get that the point corresponding to 1 is in the domain because it's the point 1, 1, but it just happens to map to what we called infinity. So if you literally plug it in, you'll get 2i 0, but that's equivalent to 1, 0, which we call the point at infinity. So under this model, 1 maps to infinity, and you can even see where the point infinity maps to. So infinity was 1, 0, and you can directly compute that that maps to I minus 1, which is equivalent to minus I. You could also see that down here with the inverse function. So minus I is not in the domain of the kind of little f, but in big F it is. I can put in minus I1, and this maps to infinity. And this is the inverse function, so it's no surprise, but you can check that infinity maps to 1. All right, I hope you enjoyed our quick introduction to fractional linear transformations, and I hope you see that by converting these transformations to this new space CP1 and viewing them as a family of matrices is really quite powerful, and we'll see that even better in the next set of lectures.